Welcome to our last lesson of Module 1, which has basically covered all you need to know about JavaScript in order to become a React professional. Learning a programming language is not just about mastering the grammar. It's equally important to study the standard library so that you're familiar with all the tools that come with the language. And for our final lesson, we'll talk more about the cool features of JavaScript's standard library. In this lesson, we're going to examine the classes and functions built into all JavaScript and available to all platforms. We're going to unpack how to handle asynchrony with events and callback functions in JavaScript. Discover how promises provide a new way of structuring callback functions, and also learn about async and await keyboards. Explore JSON and its different formats. Some data types, such as numbers and string objects and arrays, are so fundamental to JavaScript that we can even consider them to be a part of the language itself. This lesson covers all the important but less fundamental application programming interfaces, or APIs, that can be thought of as defining the standard library for JavaScript. These are useful classes and functions that are built into JavaScript and available to all JavaScript programs in both web browsers. The date class is JavaScript's API for working with dates and times. You create a date object with the date constructor. With no arguments, it returns a date object that represents the current date and time, like this. And this will return the current time. If you specify 2 or more integer arguments, they are interpreted as the year, month, day of month, hour, minute, second, and millisecond in your local time zone, as in this example. A cool quirk with the date API is that the first month of a year is number 0, but the first day of a month is number 1. If you omit the time fields, the date constructor defaults them all to 0, setting the time to midnight. When a program needs to save date or needs to transmit data across a network connection to another program, it must convert its in-memory data structures into a string of bytes or characters that can be saved or transmitted and then later passed to restore the original in-memory data structures. The easiest way to sterilize data in JavaScript is using a sterilization method known as JSON, and this acronym stands for JavaScript Object Notation, and as the name implies, the format uses JavaScript object and array literal syntax to convert data structures consisting of objects and arrays into strings. JSON supports primitive numbers and strings and also the values true, false, and null, as well as arrays and objects built up from those primitive values. JSON syntax allows the representation of 3 types of values. Simple values, strings, numbers, booleans, and null can all be represented in JSON using the same syntax as JavaScript, but the special value undefined is not supported. Objects. The first complex data type, objects, represent ordered key value pairs. Each value must be a primitive type or a complex type. And arrays. The second complex data type, arrays, represent the ordered list of values that are accessible via a numeric index. The values may be of any type, including simple values, objects, and even other arrays. Bear in mind that there are no variables, functions, or object instances in JSON. JSON is all about representing structured data, and although it shares syntax with JavaScript, it should not be confused with JavaScript paradigms. So let's take a look at each of these a little bit closer. In its simplest form, JSON represents a small number of simple values. For example, the following is a valid JSON. This is JSON that represents the number 5. Likewise, the following is also valid JSON, representing a string. The big difference between JavaScript strings and JSON strings is that JSON strings must use double quotes to be valid. Single quotes causes a syntax error. Boolean values and null are valid, as they are as standalone JSON. In practice, however, JSON is often used to represent more complex data structures, in which simple values represent just part of the overall information. Objects are represented using a slight modification of object literal notation. Object literals in JavaScript look like this. There are a couple of differences from the JavaScript example. First, there is no variable declaration. Variables don't exist in JSON. And secondly, there is no trailing semicolon. It's not needed because this isn't a JavaScript statement. And once again, the quotes around the property name are required to be valid JSON. In JSON, the value can be any simple or complex value, which allows you to embed objects within objects. Objects in JSON look like this. This example embeds school information into the top-level object. Even though there are two properties called name, they are in two different objects, and so they are allowed. You do want to avoid having two properties of the same name in the same object. The second complex type in JSON is the array. Arrays are represented in JSON using array literal notation from JavaScript. For example, this is an array in JavaScript. We can represent this same array in JSON using a similar syntax. Also note the absence of a variable or a semicolon. Since the earliest days of JavaScript, web browsers have defined two functions, setTimeout and setInterval. They allow programs to ask the browser to invoke a function after a specified amount of time has elapsed, or to invoke the function repeatedly at the specified interval. These functions have never been standardized as a part of the core language, but they work in all browsers and in Node, and are a de facto part of the JavaScript standard library. The first argument to setTimeout is a function, and the second argument is a number that specifies how many milliseconds should elapse before the function is invoked. After the specified amount of time, and maybe a little bit longer if the system is busy, the function will be invoked with no arguments. Here, for example, are 3 setTimeout calls that print console messages after 1 second, 2 seconds, and 3 seconds. Note that setTimeout does not wait for the time to elapse before returning. All 3 lines of code in this example run almost instantly, but nothing happens until the 1000th millisecond elapses. If you omit the second argument to setTimeout, it defaults to 0. Now that doesn't mean, however, that the function you specify is invoked immediately. Instead, the function is registered to be called as soon as possible. If a browser is particularly busy handling user input or other events, it may take 10 milliseconds or more before the function is invoked. Instead, the function is registered to be called as soon as possible. And if the browser is particularly busy handling user input or other events, it may take 10 milliseconds or more before the function is invoked. setTimeout registers a function to be invoked once. Sometimes that function will itself call setTimeout to schedule another invocation at a future point. If you want to invoke a function repeatedly, however, it's often simpler to use the setInterval. SetInterval takes the same 2 arguments as setTimeout, but invokes the function repeatedly every time the specified number of milliseconds has elapsed. Some computer programs run continuously, without pause, until they've computed their result. Most real-world computer programs, however, are significantly asynchronous. This means that they stop computing whilst waiting for data to arrive or for some event to occur. Did you know that some web browsers are typically event-driven, meaning that they wait for the user to click or tap before they actually do anything, and JavaScript-based servers typically wait for clients' requests to arrive over the network before they do anything. Synchronous behavior is similar to sequential processor instructions in memory. Each instruction is executed strictly in the order in which it appears, and each instruction is also capable of immediately retrieving information that's stored locally within a system, for example in a processor register or in system memory, and as a result it's easy to reason about the program state, for example the value of a variable, at any given point in code. A trivial example of this would be performing a simple arithmetic operation, like this. At each step in this program, it's possible to reason about the state of the program, because execution will not proceed until the previous instruction is completed. When the last instruction completes, the computed value of x is immediately available for use. Conversely, asynchronous behavior is similar to interrupts, where an entity external to the current process is able to trigger code execution. An asynchronous operation is often required because it's infeasible to force the process to wait a long time for an operation to complete, which is the case with a synchronous operation. This long wait might occur because the code is accessing a high latency resource, such as sending a request to a remote server and awaiting a response. A trivial JavaScript example of this would be performing an arithmetic operation inside a timeout, like this. At its most fundamental level, asynchronous programming in JavaScript is done with callbacks. A callback is a function that you write and then pass to some other function. That other function then invokes or calls back your function when some condition is met, or some asynchronous event occurs. The invocation of the callback function you provide notifies you of the condition or the event, and sometimes the invocation will include function arguments that provide additional details. We're now going to examine two forms of callback-based asynchronous programming: timers and events. One of the simplest types of asynchrony is to use the set timeout when you want to run some code after a certain amount of time has elapsed, like this. The first argument to set timeout is a function, and the second argument is a time interval, measured in milliseconds. In the example, a hypothetical check for updates function will be called 60,000 milliseconds, or 1 minute, after the set timeout call. Check for updates is a callback function that your program might define, and set timeout is the function that you invoke to register your callback function and specify under what asynchronous conditions it should be invoked. Set timeout calls the specified callback function one time, passing no arguments, and then forgets about it. Both set timeout and set interval return a value. If you can save this value in a variable, you can then use it later to cancel the execution of the function by passing it to clear timeout or to clear interval. The return value is typically a number in web browsers and is an object in Node. The only thing that you can do with this value is pass it to clear timeout to cancel the execution of a function registered with set timeout. Take a look at this example. Now, this example demonstrates the use of set timeout, set interval, and clear interval to display a simple digital clock with the console API. At the beginning, the program will clear the console and print the current time once a second. Then the last line means after 10 seconds, stop the repeating code above. An ECMA script function doesn't care how many arguments are passed in, nor does it care about the data types of those arguments. Just because you define a function to accept 2 arguments doesn't mean you can pass it in only 2 arguments. You could pass in 1 or 3 or even none, and the interpreter won't complain. This indifference happens because arguments in ECMA scripts are represented as an array internally. The array is always passed to the function, but the function doesn't care if anything is in the array. If the array arrives with 0 items, that's fine. If it arrives with more, that's okay too. In fact, when a function is defined using the keyword, meaning a non-arrow function, there actually is an arguments object that can be accessed while inside a function to retrieve the values of each argument that it was passed in. The arguments object acts like an array, though it isn't an instance of an array, in that you can access each argument using bracket notation and determine how many arguments were passed in by using the length property. In the following example, the sayHi function's first argument is named name. The same value can be accessed by referencing arguments 0. Therefore, the function can be rewritten without naming the arguments explicitly, like this. If you're writing a function that really does check for updates, you probably want to run it repeatedly, and you can do this by using setInterval instead of setTimeout, like this. In this example, the program will call checkForUpdates in 1 minute, and then again every minute after that. SetInterval returns a value that we can use to stop the repeated function. The other kind of asynchrony is events. Client-sided JavaScript programs are almost universally event-driven. This means that rather than running premeditated computation, they typically wait for the user to do something, and then respond to the user's actions. The web browser generates an event when the user presses a key on the keyboard, or moves the mouse, or even clicks the mouse button, or touches a touchscreen device. Event-driven JavaScript programs register callback functions for specified types of events in specified contexts. And the web browser invokes those functions whenever the specified event occurs. These callback functions are called event handlers, or event listeners, and they are registered with addEventListener. Look at this example. In this example, applyUpdate is a hypothetical callback function that we assume is implemented somewhere else. The call to document query selector returns the object that represents a single specified element in the web page. We call addEventListener on that element to register our callback. Then the first argument to addEventListener is a string that specifies the kind of event that we're interested in, a mouse click or a touchscreen tap in this case. If the user clicks or taps on that specified element of the web page, then the browser will invoke the applyUpdate callback function, passing an object that includes details about that event. Now that we've seen examples of callback and event-based asynchronous programming in JavaScript environments, we can introduce promises. Promises are a core language feature designed to simplify asynchronous programming. A promise is an object that represents the result of an asynchronous computation. That result may or may not be ready yet, and the promise API is intentionally vague about this. There is no way to synchronously get the value of a promise. You can only ask the promise to call back a function when the value is ready. So at its simplest form, promises are just a different way of working with callbacks. However, there are practical benefits to using them. One real problem with callback-based asynchronous programming is that it's common to end up with callbacks, with lines of code so highly indented that it's really difficult to read. Promises allow this kind of nested callback to be re-expressed as a more linear promise chain that tends to be easier to read and easier to reason about. Do note that promises represent the future results of single asynchronous computations. They cannot be used to represent repeated asynchronous computations. With the advent of promises in core JavaScript language, web browsers have begun to implement promise-based APIs. Let's take a look at how we would use this promise-returning utility function. Here's an example. GetJSON starts an HTTP request for the URL you specify, and then, while that request is pending, it returns a promise object. The promise object defines a then instance method. Instead of passing our callback function directly to JSON, we instead pass it to the other then method. When the HTTP response arrives, the body of that response is passed as JSON, and the resulting passed value is passed to the function that we passed to then. Think of the then method as a callback registration method, like the addEventListener method used for registering event handlers in client-sided JavaScript. If you call the then method of a promise object multiple times, each of the functions you specify will be called when the promise computation is complete. Asynchronous operations, particularly those that involve networking, can typically fail in a number of ways, and robust code has to be written to handle the errors that will inevitably occur. For promises, we can do this by passing a second function to the then method, like this. A promise represents the future result of an asynchronous computation that occurs after the promise object is created. Because the computation is performed after the promise object is returned to us, there is no way that the computation can traditionally return a value or throw an exception that we can catch. The functions that we pass to then provide alternatives. When a promise-based asynchronous computation completes normally, it passes its result to the function that is the first argument to then. When something goes wrong in a synchronous computation, it throws an exception that propagates up against the call stack until there is a catch clause to handle it. When an asynchronous computation runs, its caller is no longer on the stack, so if something does go wrong, it is simply not possible to throw an exception back to the caller. Instead, promise-based asynchronous computations pass the exception, typically as an error object of some kind, though this is not required, to the second function passed to then. So in this previous code example, if getJSON runs normally, it passes its result to the display user profile. If there is an error, the user is not logged in or the server is down, the user's internet connection has been dropped, the request has timed out, etc., then getJSON passes an error object to handle profile error. Now, the most idiomatic way to handle errors in this code looks like this. With this code, a normal result from getJSON is still passed to display user profile, but any error in getJSON or in display user profile, including any exceptions thrown by display user profile, get passed down to handle profile error. The catch method is just a shorthand for calling then with a null first argument, and the specified error handler function as the second argument. One of the most important benefits of promises is that they provide a natural way to express a sequence of asynchronous operations as a linear chain of then method invocations, without having to nest each operation within the callback of the previous one. Here, for example, is a hypothetical promise chain. This code illustrates how a chain of promises can make it easy to express a sequence of asynchronous operations. We're not going to discuss this particular promise chain further, but we will continue to explore the idea of using promise chains to make HTTP requests. ES 2017 introduces two new keywords, async and await. That represents a paradigm shift in asynchronous JavaScript programming. These new keywords dramatically simplify the use of promises and allow us to write promise-based asynchronous code that looks like synchronous code that blocks while waiting for network responses or other asynchronous events. The await keyword takes a promise and turns it back into a return value or a thrown exception. Given a promise object P, the expression await P waits until P settles. If P fulfills, then the value of the await P is the fulfillment value of P, and if P is rejected, the await P expression throws the rejection value of P. On the other hand, if P is rejected, then the await P expression throws the rejection value of P. We don't usually use await with a variable that holds a promise. Instead, we use it before the invocation of a function that returns a promise like this. It's critical to understand right away that the await keyword does not cause your program to block and literally do nothing until the specified promise settles. The code remains asynchronous, and the await simply disguises this fact. Now, this means that any code that uses await is itself asynchronous. Because any code that uses await is asynchronous, there is one critical rule. You can only use the await keyword within functions that have been declared with the async keyword. Here is a getHighScore function written to use async and await. Declaring a function async means that the return value of the function will be a promise, even if no promise-related code appears in the body of the function. If an async function appears to return normally, then the promise object that is the real return value of the function will resolve to that apparent return value. And if an async function appears to throw an exception, then the promise object that it returns will be rejected with that exception. Mastering asynchronous behavior inside single-threaded JavaScript runtime has long been an imposing task. With the introduction of promises in ES6 and async await ES7, asynchronous constructs in ULogicMatrix have been greatly improved and enhanced. Not only do they promise async await enable patterns that were previously difficult or impossible to implement, but they engender an entirely new way of writing JavaScript that's cleaner and shorter and easier to understand and debug. Promises are built to offer a clean abstraction around asynchronous code. They can represent an asynchronously executed block of code, but they can also represent an asynchronously calculated value. Well, I do trust that you're enjoying this journey. You are well on your way to joining the React JavaScript community, leaders in the world of web development. As you by now already know, React JavaScript has become the go-to choice for businesses and entrepreneurs because of its flexibility, simplicity, and performance. By the end of this module, you'll have all you need to know about JavaScript. Then, in Module 2, you'll be diving into the fundamentals of React. You'll build a real-world application along the way with plain React, without complicated tooling. You're going to learn so much more about the wonderful and fascinating world of React. Things like concepts and patterns, and best practices in a real-world React application. And if you haven't already, you'll fall in love with this fantastic front-end web development tool. JavaScript has traditionally been known as the most difficult programming language to debug because of its dynamic nature and years without proper development tools. The third edition of ULogicMatrix aimed to improve this situation, introducing the try-catch and throw statements, along with various error types to help developers deal with errors when they occur. Did you know that all the major desktop browsers, like Internet Explorer, Firefox, Safari, Chrome, and Opera, have some ways to report JavaScript errors to the user? By default, they hide this information because it's of little use to anyone but the developer, and because it's the nature of web pages to throw errors during normal operation. All modern desktop web browsers expose errors through their web console. These errors can be revealed in the Developer Tools console. In all the previously mentioned browsers, they share a common path for accessing the web console. The easiest way to view errors is to right-click on the web page, select Inspect or Inspect Element, and click the Console tab. To use a shortcut to proceed directly to the console, different operating systems and browsers support different key combinations. Here they are. Oh, and you might want to snap and save this to refer back to at any time you'd like. I'll give you a couple of seconds. And moving on. No one doubts the importance of error handling in programming. Every major web application needs a good error handling protocol, and most good applications have one, though it is typically on the server side of the application. Error handling has been very slow to be adopted on the browser side of web applications, even though it's just as important. An important fact to understand is that most people who use the web are not technically savvy. They don't even fully comprehend what a web browser is, let alone which one they're using. ECMA Script 262, 3rd edition, introduced the try-catch method as a way to handle exceptions in JavaScript. The basic syntax is as follows, which is the same as the try-catch method statement in JavaScript. Any code that might possibly throw an error should be placed in the try portion of the statement, and the code to handle the error is placed in the catch portion, as shown in the following example. If an error occurs at any point in the try portion of the statement, code execution immediately exits and resumes in the catch portion. The catch portion statement receives an object containing information about the error that's occurred. The exact information available on this object varies from browser to browser, but contains at minimum a message property that holds the error message. ECMA 262 also specifies a name property that defines the type of error. This property is available in all current browsers. You can therefore display the actual browser message if necessary, as shown in this example. The Fetch API can perform all the same tasks as an XML HTTP request object, but is much easier to use, has a more modern interface, and is able to be used by modern web tools like web workers, whereas the XML HTTP request is optionally asynchronous. All requests dispatched by the Fetch API are strictly asynchronous. The Fetch API itself is a superior tool for requesting resources in JavaScript, but the API is also relevant in the domain of service workers, in that it provides an interface for intercepting, redirecting, and altering requests made via Fetch. The Fetch method is available in any global scope, both in the primary page execution, models, and inside workers. Invoking it will instruct the browser to send a request to a provided URL. The fetch method has only a single required parameter input, which most of the time will be the URL of the resource you wish to fetch. This method returns a promise like this. The interpretation of this URL, relative paths, absolute paths, and so on, is performed identically to that of XML HTTP request API request. When the request completes and the resource is available, the promise will resolve into a response object, which is used as the API wrapper for whatever resource is fetched. This object exposes a number of properties and methods to inspect the response and convert the payload into a useful form, as shown in this example. Now, the simplest way to read the contents of a response is in the raw text format, which is accessed using the text method. This method returns a promise that resolves with the full contents of the fetched resource. Take a look at this example. A simple JSO string can be sent to the server as follows. Axios is a very popular JavaScript library that allows you to make HTTP requests to a RESTful or a GraphQL API. Axios accomplishes the same task as the Fetch API, provided by many web browsers. To use Axios, you need to have Node.js installed on your computer. Then you can add Axios to your project. To accomplish this, you just run the following command in your terminal. And the main advantage of using Axios instead of the Fetch API is because it provides a very clean and precise syntax. Take a look at this example. Here we set the URL as a variable and then pass it to axios.get and set the .then callback to console the data that gets returned from the request. If we use Fetch, there is a two-step process when handling JSON data. The first step is to make the actual request, and then the second step is to call the .json method on the response. You can write the previous example using fetch like this. That's great, but this is not the data that you're looking for. This is the response from the server letting you know that your request went through just fine. Great, but you can't really do much with that. To get the data, you have to pass it to the .json first, and then you can see it. So by using Axios, you can cut out the middle step of passing the result of the HTTP request to the .json method. Axios returns the data object you would expect.